So this is the first meeting of the Vertical Flight Society History Committee meeting for 2022. And our guest speaker today is Erasmo Pinheiro. He is active in the History Committee and works for Bell. And we're just excited to hear about his presentation entitled the Bell Aerosystems X-22A as a VTOL research tool. And this is an introduction. So Erasmo, over to you, sir.
Thank you very much. Well, first of all, Happy New Year to everyone. It's been an incredible 2 or 3 years, but here we are in 2022 trying to make the best out of it. So thank you so much for your participation, and thank you for inviting me to this presentation. Yes, this topic is very dear to me. I fell in love with this aircraft a long time ago, but I never really have been able to really dive in it the way I always wanted to. I visited the Niagara Aerospace Museum like 15 to 20 years ago, and I got to see the aircraft there on display, the only remaining prototype of the 2 that they built. And the aircraft since then has been dismantled and taken away from the museum, apparently to give the museum a little bit more space, and is now in storage in Niagara Falls in Buffalo. It's still there, and I'm going to cover that in my presentation, but the bottom line is that I saw the aircraft fully assembled. I never saw the aircraft flying, but I always fell in love with this aircraft from day one. It is an incredible machine. It has done a lot of great things for VTOL, especially in the areas of operations and piloted control VTOL aircraft. And I'm going to cover that a little bit more on my presentation. Next slide, please. I don't see the slide, by the way.
No, you don't. Let me see where it went. There we go.
I see the cover slide. Now I see the slide. Thank you. Okay, so in the 1950s, as we all know, the missiles and the nuclear strategy of the beginning of the Cold War was king. And the services were vying against each other, trying to outdo each other when it comes to funding, when it comes to nuclear strategy, and some of the things that they had to do. We all know the history behind the Navy and the Air Force and the competition they had for nuclear supremacy. And that created a lot of issues for the aeronautical community, because the aeronautical community at the time felt that even though they were building fighters and they're building all kinds of interesting aircraft, when it comes to rotorcraft and VTOL and things like that, they were kind of being overshadowed by the nuclear strategies and the things that were important at the time. Well, some of the officials in the Pentagon were not like that. They were interested in some strategies in the Pentagon were thinking, well, that is all great, but if we have to go in Europe and fight a war against the Soviets in Europe, or if we have to deploy forces on aircraft carriers and take them away from the mainland and to do invasions and so forth, we're going to need aircraft that are able to take off vertically and land in small places or in runways that have been destroyed by the enemy. So they began to push that idea together. And aerospace companies, as you know, they keep in touch with the Pentagon and they do have connections. And they also realized that the Pentagon was interested in VTOL aircrafts, and they began to do their own research on VTOL machines. Again, I'm talking about early 50s to late to mid 50s here. Next slide, please. So yes, just like I said, the aircraft companies were not oblivious to this environment, and they began to do their own research and testing. For example, in the UK, the Harrier or the Hawker P1127 began to fly early. And those things were, as you know, became very successful VTOL aircraft on their own right. The Convair Pogo was the first vertical takeoff aircraft that did a transition from vertical to horizontal and back to vertical. And the VertiJet also was the first jet aircraft that flew vertically under his own thrust. So all these things were going on. And in the background of that, the Pentagon began to look at, with the Navy as the main proponent there, began to look at something called the Tri-Service Assault Transport Program. But before they did that, they went ahead and contacted a professor at Princeton University. To go to the next slide, I'm going to show you what I mean. I got them a little bit out of order, but let me say this. The Tri-Service Program was the catalyst for a lot of the VTOL aircraft that we got to see in the 1960s and early 70s. And the Tri-Service Program was very much interesting to the aircraft companies. In fact, in the list that you see there on the slide, those were the companies that vied for the Tri-Service Program. Actually, there are more than that. There's only about 10 of them. I'm sure there were at least 11 or 12 of them that participated in submitting proposals to the Navy, to the Bureau of Weapons. But let me go to the next slide to show you what I mean by that. This whole thing began, like I said earlier, as a Pentagon initiative. They approached Professor Cortland Perkins at the University of Princeton University. Dr. Perkins, if you study aeronautical engineering, by the way, you probably use some of his textbooks. Dr. Perkins was a very well-known figure in the aeronautical academic world back in the 1960s, actually even the 50s. So the Navy approached him and say, Dr. Perkins, I want you to do a study, convene a conference, and let us know whether the technology of VTOL aviation or VTOL engineering is up to the task to be able to do this Tri-Service Program that we want to pursue. Before we even send out a request for proposal, we want to know that this is actually viable. Well, Dr. Cortland Perkins went away and he did his own research on it. He convened, he talked to many experts. He had a small conference in Princeton about it, and he put out a report. And the report concluded that indeed the technology of the industry at the time had the right level of maturity to pursue this program. And sure enough, the Navy took his word for it. And in 1961, they submitted an RFP. And you can see that in the block diagram. As you can see, it's going down the arrows. Follow the arrows with me if you would for now. Well, like I said on my previous slide, about 10 different proposals from aircraft manufacturers were presented. And by the way, these proposals were not built or were not drafted in a vacuum. NASA provided some input, and you see that with the yellow box there on the right. And the Navy also was managing that, the proposal initiative there. And the rules were, or one of the basic rules of that requirement of the RFP was that the aircraft had to be able to have a gross weight of 35,000 pounds. Again, that's a big deal back in those days when basically probably no VTOL aircraft was capable of lifting itself off the ground, much less, you know, a 35,000 pound gross weight class. Anyway, a lot of if you look at the proposals of each of the contenders there, we have a mixture of configurations. We have tilt props, tilt wings, tilt rotors, tilt ducts, and so on and so forth, and a combination of those. The Navy Bureau of Weapons looked at all those proposals and determined that none of them, and I want to stress that word, none of them met the requirements. Of course, that wasn't surprising. It was a big challenge to be able to, you know, have a 35,000 pound gross weight aircraft to do all that work, especially vertical takeoff. So, but let's go to the next slide and see where that leads. Okay, So the Navy Bureau of Aeronautical Weapons determined, like I said, like you see that on the top left, that none of those vehicles met the requirement. So they went ahead and decided to split the program into two. They told the Navy, okay, you Navy, I know you began this whole process, but I want you to go on your own and to see if you can meet your own needs, which are a little bit less stringent than the ones that we have. So the Air Force took, and the Army took over the one half of the program, of the tri-service program, and the Navy took control of the other half. In the Air Force half, the Air Force funded LTV and Curtiss-Wright to do the X-19 and to build the XC-142. And I'll talk about that later a little bit more. And they were managed by the Air Force. The Navy, on the other hand, got together with NASA, and they told NASA, okay, NASA, you know a lot about VTOL. I want you to help me manage this steel duct configuration that I like so much, because they have been working with Bell for a while on this anyway. And I would like to add, on top of the requirements that we have, I would like to be able to have a vehicle that can do variable stability research. In other words, to be able to configure the aircraft in flight to simulate other types of aircraft. Because what the Navy wanted, they wanted to be able to do more research before they commit to a particular configuration. And they figured that a ducted VTOL aircraft was going to be able to do that, especially if they lowered the gross weight to 14,000 pounds like they did. That makes things a little bit easier, and they began to manage that program. So the Navy awarded the contract to Bell in November 1962, but that wasn't that. The Bell at that point was competing with Douglas on the Model A-28, and Douglas had also came up with a ducted configuration, just like Bell did. Well, the Pentagon got themselves into a box, because a lot of politicians got a hold of that decision, and they began 3 days of Armored Services Committee hearings in June of 1963, trying to figure out why the Navy gave the contract to Bell. Obviously, that is not something that anybody wants, to go through 3 days of hearings, explaining themselves of why they selected a company that in the first place was not recommended by the Navy. The Navy actually decided that the Douglas design was better than Bell, but the Pentagon still gave the contract to Bell anyway, and that's what triggered the whole situation here with the Armed Services Committee hearings. Obviously, I'm sure that Douglas has something to do with it. I don't have the proof, but I'm sure they called their senators and they began to complain of why, if the Navy selected them as the best technical solution, why did Bell get the contract? But let's leave it at that. Let's go to the next slide. You can go into the internet and download the transcripts of the hearings, which occurred on the 12th, 13th, and 14th of June of 1963. I'll tell you what, guys, I went through the first few pages, and it's fascinating. It is fascinating how the politicians and the technical folks and the military folks began to, go to these hearings and expose their reasons why they did what they did. And it was a very interesting example of how the industrial military complex deal with each other when it comes to contractual obligations and contractual decisions. It is really a case study on how these things happen and why they happen. But in any case, in these hearings themselves, big names like Barry Goldwater and a few others incredible and famous politicians, or soon to be famous politicians, were part of the Armed Services Committee, and they asked questions and they got answers. Anyway, if you can download it, I'm going to leave that to do in your own and read it. It would make really fascinating reading if you don't have anything else to do. Next slide, please. So again, I want to show pictures of the two aircraft that were managed by the Air Force, the Curtiss X-19 and the XC-142. Obviously, I got presentations on both of these aircraft that I have given in the past to other meetings and other clubs and things like that. Maybe in the future, I can go ahead and bring them on, present them to you. But these two aircraft alone will take 2 or 3 hours just to talk about them. They are very interesting technically and historically. So I'm going to go ahead and leave it at that. Next slide, please. So I'm going to show a series of slides, and I'm going to go very quick, Bob, showing on the next 7 slides artistic renderings of what those competitors before the were during the tri-service program RFP, or the request for proposal. And mainly a lot of these pictures and should I say renderings come from a very good paper that NASA put out. It's NASA Technical Memorandum 2017. If you download that from the internet, very easy to do. It's a very nice read because it's a paper about how the controls or the pilot controls were designed for each of these aircraft. It's a very interesting paper, but it happens to have pictures or drawings of the contenders, and it's very hard to find that information in one single paper. Next slide, please. This is the Douglas entry for the tri-service program. It had 2 types, a ducted version and a tilt propeller version, the A29 and the A28. Next slide, please. This is the Sikorsky entry to the program. It was a tilt wing. Believe it or not, Sikorsky also dealt with the tilt wing designs, not only on this program, but in other programs that I've been exposed to when I was working at Sikorsky Aircraft. Next slide, please. This is the North American Aviation tilt wing design. Notice that it had a ducted lift tail propeller in the back that was used for pitch control during hover. Thank you, Bob, for helping me with the slides. I really appreciate that. Next slide, please. This is the McDonnell 175 design or configuration. It's basically a tilt wing. They even actually went as far as putting a model on the wind tunnel. And you can see that picture right there on the right. Not only did they propose a tilt wing aircraft, they also proposed a tip jet helicopter called the Model 177. I don't have a picture included in here, but it was an incredible program that I would like to cover one of these days in another presentation. It's really a very interesting program for a compound helicopter. Next slide, please. This is the Boeing Vertol 137 entry to the tri-service program. It's also a tilt wing. Notice that they actually went ahead and did a wind tunnel model, a power wind tunnel model to study the characteristics of tilt wings. Next slide, please. Boeing also had another program out of the Wichita division where they actually had a big transport that had a series of ducted fans on the fuselage and 2 jet engines for cruise control or cruise power. And there you have it, some dimensions. They're very hard to read, but it just gives you an idea what the aircraft looked like. It was a canard configuration, one of the early canards aircraft ever. So it's very interesting in itself. Next slide, please. Now, Bell, on the other hand, way back in the 50s, they were already messing around with ducted fans. And they actually did testings at the University of I think it was Wichita University, someplace like that. And they actually built some wind tunnel testing too. But the bottom line is that they did a lot of research on ducted fans, and they even put out a model called the 2022 model to respond to an Army and Marine request for proposal way back in the 50s. In the end, this is what the tri-service entry for Bell was. They never got to build it. They never got the contract, but that was their entry. Notice that they collaborated with Lockheed on this particular tri-service proposal response. You can see in the tail there, it's hard to read, obviously, but if you zoom into it, the logo of Bell, Aerosystems, and Lockheed together in one. It's probably the only time you're going to see that type of logo in one aircraft, Bell and Lockheed together. Anyway, this particular design that they were tinkering with in the 50s became the 2064 tri-service configuration entry to the tri-service program. Again, as you all know, and I mentioned that earlier, the X-19 and the XC-142 from LTV were the ones that got selected to continue on in prototype form for the tri-service program. Next slide, please. So let's talk about the X-22, how the Navy managed program. Remember that the program is split into two halves. Now we're going to concentrate on the half that was managed by the Navy with NASA oversight. Next slide, please. So Bell Aerosystems put out a model 2127. It was a research vehicle. It was all on paper. And they, like I said earlier, they were evaluating this between 1953 to 1959. They even had a twin ducted aircraft called the Model D-190 that was also proposed as a solution for what the Navy wanted. At the end, they selected a four ducted configuration. And on the left, you see an artistic rendering of the aircraft before it was even built. And on the right, you'll see the rollout ceremony of the X-22 on May of 1965, 25th of May, 1965. It was unveiled in Whitfield, which is Niagara Falls, New York. And as you can see there in the picture, it was well attended by Navy folks, Navy officers, and company officials and Pentagon officials. The technical director for the program was Mr. Vincent Paksha, which I've never been able to find a picture of him. I wish I could. If you guys have any pictures of Mr. Vincent Paksha, I would love to get that. And the same with the project director, Joseph Marchese. I don't know how they look like. I wish I had a picture because I like to recognize the folks that were in charge of these complex programs. Again, this configuration 2127 evolved into the Bell 22 Alpha. Next slide, please. This is a picture of what the Navy envisioned as the follow-on to the X-22. I like to put this here because I don't want you to lose sight of the fact that the Navy was not doing all this research and spending all this effort and all this money just to do research. They really wanted an aircraft that could come in and bring in supplies, bring in people, bring in troops or whatever it is to the aircraft carriers in the middle of the ocean in a safe vertical way. And that's what the Navy wanted to see at the end of all this work that they were doing. It never really happened, but I just wanted to show you what the Navy folks were thinking for the future. Next slide, please. So why did Bell selected the ducted fan as their preferred configuration? Well, I got a red circle in there. Notice that, as you well know, the VTOL family is very diverse, and from helicopters all the way to aircraft like the Harrier of the F-35. That is the beauty of our profession. Our profession and our the stuff that we like is so diverse that we can spend 40 lifetimes studying all these configurations. It's really exciting. So we're just going to concentrate on the ducted fan for now. Next slide, please. So what makes a ducted fan so interesting? Well, it has to do with aerodynamics and how the propeller works. On the left side, you see a typical propeller there on the top there. And when the propeller is on the ground, let's say, imagine yourself being in a turboprop aircraft, right? Sitting on the ground, you're not moving, you're just on the ground. The propeller is very inefficient because there's a lot of spillage around the tip of the propeller. In fact, if you look at that red circle that I have there, there's even an inflow of air into the tip of the propeller downward. So all that air and all that loss is manifested in the fact that the propeller in an open condition like that is not very efficient. If you put a duct around it, okay, then you can entrain the air into a more efficient way, and you can get, and all those tip losses are reduced. In fact, you can increase the thrust of the propeller by about 25 to 30% by just putting a duct around the tip of the propeller, just like you see there on the bottom left, okay? Now, obviously, you're gonna think, well, in engineering, not everything is perfect. There's always gonna be some losses and something that you have to compromise on. And that is the lip effects and the boundary layer growth inside the duct that can create noise. It can create structural issues, aeroacoustic issues with the tip of the propeller. In fact, the Bell X-22, and I'm going to talk about that later, had a lot of issues with that, and they really became a problem for the program until they got it fixed. So those things cannot be totally ignored, even though you're getting about 26% better efficiency against an open propeller. They still have issues, and I'm going to cover that in a second. On the right side, you see another great thing that the ducted propeller does. When you're in hover, like in the X-22, supposed to hover, right? You have lift coming out of the lip of the duct because some of the aerodynamics of a ducted propeller induces a lift on the nose of the airfoil-shaped duct that tends to lift the aircraft off the ground. That's how you get the 25 to 30% more lift when you're hovering on a ducted propeller. Now, when you're cruising around and you're flying like an airplane, if you can tilt the ducts a little bit, it doesn't have to be like the angle that I showed down there, which is about 45 degrees. Even a small 2 or 3 or 4 degrees of inclination of the duct will provide you enough lift. Like if it was a ring wing, it becomes, instead of a normal wing, it becomes a circular or ring wing, and it can create lift just like any other aircraft. In fact, when the X-22 was flying in airplane mode, in other words, with the ducts completely rotated forward, it will behave like a normal aircraft. And it was fantastic to fly according to the pilots. The pilots were able to take off like an airplane. They were able to land like an airplane without any issues at all, just like it had a long wing. It was really amazing how these duct rings actually work. Next slide, please. However, just to close this issue about the ducted propellers, it has advantages and it has disadvantages. And you can see on the left side that it has advantages. You can make the propeller smaller because you don't need a big propeller to get the same thrust, okay? The tip issues that I talked about, they get mitigated or they get reduced. The thrust to weight ratio is bigger, like 25% or more, okay? Compared to a large propeller that is unducted. It's safe for the people on the ground. If you're around the aircraft, you don't have to worry about going inside a propeller. I remember when I was in the Navy, we had an E-2 running on the flight deck, and one of the ground personnel, which used to work for me, by the way, I remember him like it was today. It breaks my heart every time I think about it. He actually walked into the propeller of the E-2 on the flight deck, and they were not able to find any pieces of him any bigger than about 2 feet. And I know this is kind of gory, but the reason why I tell you this is because walking into a propeller is a very serious thing, and it happens at least once a year to somebody. It is something that is very dangerous, and to have a duct around it, it really makes a big difference, okay? Also, noise attenuation. When you have a propeller inside a duct, you tend to attenuate the noise quite a bit. But those aeroacoustic effects also have some structural issues that I'm going to cover on the right side there. Also, you have to worry about when you're flying any VTOL aircraft, the location of the CG is very important. Well, on a ducted configuration like the one on the X-22, they had a very wide CG range, and that's good for cargo. And you also, the beauty about ducting is that when you move the throttle, the propeller tends to give you a very quick thrust response because it's ducted, and all that thrust is available to you for controlling of the aircraft. Now, if you look at the right side of the table, you see some of the bad things about a ducted propeller. You have more weight, obviously. You have more drag because you have a duct that is kind of draggy, okay? It's complex. You got to worry about drive shaft, gearboxes, you know, redundancy and all kinds of things. It makes the access to the propeller and to the gearboxes a little bit more difficult. You got to take the duct out and things like that. And you get noise on the tips due to the boundary layer separations and aeroacoustics and some of the issues that I told you about, the structural issues. So don't think that all the good things about the duct is everything. Oh, it's a final answer to everything. There's always something that you have to compromise on. Next slide, please. And when it comes to hover, the ducted fan is kind of in between a helicopter and a Harrier type of aircraft, as you can see there on the red circle there. It's actually closer to a tail wing. If you have to compare one to the other, it's probably a more fair comparison to compare it to a tail wing aircraft than any other type of aircraft. Next slide, please. When it comes to fuel consumption, in other words, your efficiency to be able to reach long distances, to be able to carry more things or whatever, the ducted fan is kind of in between too. It's not a perfect solution for everything, okay? When it comes to fuel consumption, probably a rotor, like a regular helicopter or a tilt rotor might be best for that kind of thing. Next slide, please. Ducted fans. Ducted fans attracted the attention of many researchers, including NASA. And NASA did a lot of testing of ducted fans, including testing for the DOAC VC4, which is another ducted fan aircraft. And I'm going to cover that in a second. Notice how NASA, you can go into the internet and, for example, you can look at NASA technical note 1301 from 1962, and you'll see a lot of data, lots of data about ducted fans. So ducted fans were very well investigated in the 1960s, not just for Bell, but also for DOAC and other companies too. It was a very attractive propulsor, should I say, a very attractive way of being able to control thrust and provide thrust to an aircraft in a more efficient manner, better than a regular propeller, okay? Next slide, please. This is the wind tunnel model of the X-22A that was tested at NASA Langley. Okay, they also did a 1/16 scale model test at the David Taylor Model Basin in Washington, D.C. By the way, if you never visited that facility, I would recommend you that you do. I did, and it was really an eye-opener. It is a national treasure. Go ahead and look into it, and you see what I mean. It's really amazing. Go online and research that, and you'll be surprised. Next slide, please. So Bell built a mock-up. Here's a mock-up of the cockpit. Very kind of primitive, but it gave the pilots a sense of where things were going. Notice that it had a clamshell type of access to the cockpit, very convenient. The visibility was great. The pilots loved the visibility of the aircraft, especially since the aircraft with the two pair of ducts didn't have to really raise the nose too much or lower the nose too much. It was almost flying always at a very level attitude, and that it was good for the pilots. They love, and when it comes to a VTOL aircraft, it's good to be level. You like to be level, and that is what the X-22 provided the pilots. Next slide, please. This is a drawing showing the major characteristics of the aircraft. Notice that it have 4 ducts, 2 in the front, 2 in the back. When you look at the aircraft from the front, notice that the 2 ducts from the back were kind of outside the exhaust of the 2 ducts from the front. That way they didn't complicate the aerodynamics too much. Also, the rear wing also provided a little bit of lift, obviously. The rotor, it didn't have an elevator per se, but it had a big vertical rotor because this aircraft, ducted aircraft like this, they do have something called a side force. The side force is a problem when it comes to hovering and controlling an aircraft in yaw and things like that. So that is one of the things about this aircraft. Bell decided to put a large vertical tail there because they wanted to make sure that they had enough control in the yaw axis to make sure that the aircraft were going to be stable enough. Remember, this aircraft was supposed to be a research aircraft, so you wanted to make sure that the aircraft had very benign and good flying qualities, level 1 type of flying qualities, which is the best you can get. Okay, next slide, please. This is a picture of the cockpit. Very conventional for the time, no glass cockpit like today. It was all gauge type of instruments. Okay, now notice that in the center there, Bob, if you'd be so kind to point to it, there are 4, there you go, right there. There are 4 controls for the ducts. You can link those thrust levers to the ducts, and when you push them forward, the aircraft will climb like a helicopter. When you push them back, or when you pull them back, it will descend the aircraft like a helicopter. It also had a control stick like an aircraft, because remember, this aircraft was going to fly like an aircraft after you take off. So it will behave like a normal aircraft, and you use the control stick like you would normally. But the good thing is that it had a stick, a collective stick like a helicopter also. You don't see it very well in this picture, but it had a collective stick to be able to lift it up like a regular helicopter too. And the collective stick was linked to the throttles that Bob just pointed out to, and those were connected together. So in the top panel there, if you, Bob, if you can move up to the top there, that top panel is designed for the variable stability system of the aircraft. In other words, a lot of the variable stability equations and models were put on the aircraft using those parameters, and that's how the aircraft was able to simulate the different type of aircraft that were not like the X-22. The left pilot will be the guy testing the unknown or the fictional simulated aircraft. The pilot on the right, or the guy sitting on the right, was the safety pilot. In other words, he was in control of the aircraft at all times. If the other pilot will make a mistake or the aircraft will behave in a weird way, the pilot in the right seat could take control of the aircraft very quickly and stop the simulation and being able to put the aircraft back the way it was. So it was a flying research simulator or laboratory. Next slide, please. This is a picture of the aircraft. You have 4 T-64 engines. It was a very T-64, I don't remember the number. I forgot the engine designation right now. It doesn't matter. You have 4 turboshaft engines that were connected by shaft to the propellers in the front and the back. You can see the shaft there in the front, and you can see the one running along the fuselage through the ceiling of the roof of the cargo area. And then you have more shafting and more gearboxes in the back. Now, the picture is because I want to tell you, I'm putting together 2 papers, one for the forum coming up next year, not this year, next year, and another one for the forum in the forum A0, the forum 80 in 2024. So I'm going to try to write 2 papers. One that will deal, the first one is going to deal with the gearboxes and the drivetrain and all the things that this aircraft had. And the other paper will deal with the variable stability system of the aircraft, which I'm going to cover on the second paper. That is my goal. The reason why I mention it is because I want to show you, as part of the committee, I want to tell you what my plans are, but also it depends on what kind of information I can research or uncover when I do this type of work. It will depend on that, but I'm making some progress and I'm going to show you something later. Next slide, please. How did the aircraft control itself in roll? Well, yeah, remember, you hover and it was like an airplane. In hover, in order to roll control, you will change the pitch of the propellers on both sides, and that way you can create some roll. In an airplane mode, all you had to do was to move the elevons that you have behind the ducted fans, and that way you can control the roll like any aircraft. You can basically do this, okay? And you can do roll control very easily, okay? Next slide, please. In pitch, basically it's just like a regular aircraft in flight. You will lower the elevons in the back and the aircraft will pitch accordingly. In the hover mode, the aircraft will reduce the pitch in the front on the propellers, and the aircraft will dip itself. When the aircraft wanted to lift the nose up, it will increase the pitch in the front ducted propellers, and the aircraft will come back up like that. So by reducing the pitch of the propeller in hover, you can move the aircraft up and down, okay? Did you guys see my hand as I showing this with my hands? Yeah, okay, great. Okay, next slide, please. So when it comes to yaw, which is probably one of the most critical or tricky ones, basically what they did is they reduced the pitch on either side, and you can yaw the aircraft accordingly, okay, in hover, okay? I apologize, in cruise flight. In hover, you basically will change the elevons in different directions like this. And when you move the elevons, because the ducting is pointed down, you can actually, if you move the elevons differentially like this, you could actually rotate the aircraft in yaw, okay? And that was how they did it in hover. Next slide, please. This is a drawing showing the envelope of the aircraft. It was a very capable aircraft. It could go all the way to 2.5 Gs, okay? It didn't handle 0 G or below 0 or negative Gs too well, but it was able to go up to 195 knots in level flight, okay? It could fly rearward. It could fly, like a regular helicopter, basically. If you read the pilot comments, it was a wonderful aircraft to fly. It was better than a helicopter. It could be learned very quickly. You could take a guy, anybody, I can take you guys, and I can put you in the cockpit of it. And within 1 hour or 2 hours of flight time, you could become proficient on the aircraft, and you could actually fly it. It was a very easy aircraft to fly. In a helicopter, as any helicopter pilot will know, like Paul Fardink, who is a helicopter pilot, it takes a lot of, you almost have to be born with that instinct to be a helicopter pilot. It's not easy to be a helicopter pilot. And it takes a lot of work to become a good hovering pilot. In other words, to be able to hover a helicopter, it takes a lot of training, a lot of effort, and you almost have to be born with it. In this aircraft, you could take an air pilot who has never flown a helicopter, and they did that with 2 Navy fixed wing pilots from Pax River. They brought them over to Washington, to New York, and they put him in a simulator for about an hour. They took him to the aircraft and they gave him an hour introduction flight, and the 3rd hour they were flying by themselves. I mean, that's how quickly they learned how to fly this aircraft. It was a very benign machine to do research. Next slide, please. The aircraft itself, like any tilt wing aircraft, tilt rotor or tilt duct or tilt prop, it has something called a flying corridor, a transition corridor. It is an area of flight in the envelope where you would like to be when you're going from hover to cruise flight or from cruise flight to hover, and you like to maintain yourself in that particular corridor. That big black line that you see there, Bob, if you'd be so kind to kind of show it, that big black line is where the aircraft would like to be, the X-22 in this particular case, in order for you to be able to transition from hover to flight to regular flight, and from cruise flight to hover. Notice that the axes are the duct angle on the left, on the y-axis, and on the x-axis you have the airspeed. Notice that for 90 degrees, which is all the way to the top on the y-axis, the speed is basically zero, like you will expect it to be. When you go down the axis to, let's say 20 degrees of duct angle, you go across to the right, and it's about 100 knots, which is where you want to be. So you want it to be at 100 knots aerospeed with 20 degrees angle of a duct, okay? Now, this aircraft had some automatic stability to be able to allow the pilot to manage that a little bit, but I'm not sure about that yet. I'm doing a little bit of research on the aircraft to figure out whether the pilot actually had to go through the corridor by doing all this himself, or if the aircraft had a automatic computer, and let's call it an analog computer, to be able to handle this corridor without the pilots having to worry about it too much. So I need to do more research to find out whether that's true or not, okay? But anyway, I wanted to show that. Next slide, please. This is a plot of the hover performance of the aircraft, and basically it's all based on flight tests. It basically tells you that the aircraft could hover if you lose one duct. Let's say one duct or loses power for whatever reason. You still have 3 other ducts. Well, you are able to hover with 3 ducts, only 3 ducts. That was a safety feature that was designed on the aircraft. Obviously, when you impose something like that on an aircraft, you reduce the hover performance of the aircraft. That's why, in order for you to fly in a condition where you can lose an engine and still be able to hover, you cannot increase your maximum gross weight to more than 16,700 pounds. So the aircraft was never able to really fly to 21,000 pounds or whatever, even though it could, because of safety reasons. Next slide, please. This is a picture of the variable stability system of the aircraft. And I'm not going to dwell into this. I just want to show you a picture of it. This is going to be the theme of my second paper. I'm going to go in there and I'm going to try to understand what they did to get all this squared away. It is really an amazing idea. The engineer that came up with this was really good. There were a couple of guys, but it was mainly one guy. And is what made this aircraft a very useful VTOL research tool. So I just wanted to show you a picture of what I'm going to be talking about on my second paper. It's going to be highly technical in many ways, but also it's going to be historical because it really deserved a lot of attention. It was one of the first in-flight aircraft simulators ever. One of the first fly-by-wires aircraft. You know, it had a lot of firsts, and we need to cover that from the historical point of view. Next slide, please. This is a good picture that shows the aircraft from the bottom, and it has I wanted to highlight a couple of features. Notice that the engine exhausts are deflected downward, which increased the thrust of the aircraft vertically. It created about 600 pounds of 400 to 600 pounds of thrust in the upward direction. So it helped the hover a little bit. Notice the elevators that I was talking about earlier when it comes to flying control, so controlling the aircraft in flight. And it also had a system in the nose that was designed to be able to detect the airspeed of the aircraft in hover down to 0 airspeed. In other words, the pilots love this particular instrumentation because they were able to tell whether the aircraft was flying backwards or forward or sideward down to 1 knot of airspeed. I mean, very accurate indications of how the aircraft was behaving in hover. In a regular helicopter, you have to depend on visual cues to be able to know whether you're moving sideways or descending or climbing or whatever. with this particular instrumentation, you could look at a gauge and you could tell what exactly we're doing in hover. And the pilots love it. In fact, they never flew. If the system was down or it didn't work right, they didn't even fly. They say, I'm not going to fly this aircraft unless this instrumentation is working in good order. I mean, that's how good this was. Next slide, please. The first prototype had a crash. Remember, they built two of them. One of them survived and the other one crashed. This one is the one that crashed. It was prototype 2020. And it crashed on the 15th flight after it had accumulated about 3.2 hours of flight. The pilots were Mr. Keiko and Mr. Miller. It was the first time a VTOL aircraft is able to do an emergency landing, a successful emergency landing, and transitioning from cruise flight to vertical flight in doing that emergency. So that alone is a very historical thing. And as you can see, the aircraft was able to get to the ground, a little bit of a hard landing, but the aircraft came down fairly intact. The pilots were not hurt, but the aircraft was damaged enough for not pursuing any more flight on the aircraft. They did not repair it, but they used the cockpit area as a simulator after the crash. Next slide, please. When the aircraft was testing, even when the aircraft was already testing and flying, NASA conducted more testing of the aircraft in the 40/80 wind tunnel at NASA Ames. Again, the Navy still have hopes for building an aircraft like this to be able to use them on aircraft carriers. Remember that picture that I showed you early on, showing you how the Navy envisioned to have an aircraft like this? Well, NASA was helping the Navy understand this particular type of vehicles. Okay, next slide, please. Let me talk about the other ducted fan aircraft that were also flying or trying to fly at the time. Next slide, please. Well, the two more famous, one of them is the DOAC VC4, which, by the way, was a very successful flight test program is in its own right. And the difference here is that it had tip-mounted or wing tip-mounted ducted fans, okay? Anyway, this aircraft survived. It never crashed, really, and it was a very successful test program. Next slide, please. The other one that wasn't that successful, the other ducted VTOL aircraft that was not successful, was the French Nord Aviation N500 Cadet. You can see a picture of it there doing tether hovering. It didn't really fly on tether, I believe, ever. But it was supposed to fly on tether. Maybe the stability issues that they found during tether testing dissuaded the French to conduct regular flights with it, but who knows? I know very little about the aircraft. I have a lot of books in my home that deals with this aircraft, but I have to do a little bit more research on it. Next slide, please. This is a picture of the surviving X-22. It is now on storage at the Calspan Corporation in Buffalo, New York. You can see some pictures in there. Notice on the right-hand side, lower picture, Bob, if you'd be so kind to point to those vortex generators on the lip of the duct. If you can say you're right there. Those are the vortex generators that were included in the ducted fan to reduce something called duct buzz. That buzzing separation that was occurring at the lower lip of the duct, especially at a high angle of attack, created a lot of issues for Bell in trying to control these structural issues they had on the duct. And I'm going to cover that on the paper when I write the paper next time. I just want to give you a primer on it. Next slide, please. So we're back to the future in a way. There's a lot of companies up there that are really trying to learn from the past and apply this ducted fan technology to future air taxis, especially now that we have electrical power available to us. Companies like Bell with the Nexus and Airbus with the City Airbus and XTI are very much invested in this type of configuration. So in a way, all that effort that was done by the Navy and by those pilots and by Bell in learning from this aircraft has not totally been wasted. Apparently that configuration has a lot of attractiveness to continue to be used today. Let's make it clear that Airbus already apparently have flown the one that you see at the bottom on the right, has flown that aircraft already in hover, I believe. So it is a very real thing. And notice that the configurations of this aircraft are similar to the one on the X-22. Next slide, please. Now, I told you about my papers. I'm going to be writing papers. Notice that this is my home, a picture of my house. I am there on the right. You can see me on the bottom. There's sitting down and looking at a drawing. Those drawings are blueprints from the Niagara Falls Aerospace Museum in New York. I was able to get them to send me a box full of blueprints, and you can see the box there on the top left. Those drawings, I got to go through all of those drawings, which, by the way, they are like, I forgot the size of the drawing, but they are big. And I got to go through all those and study them and read about them and learn about the X-22 from the engineer's point of view, right? Learn about the gearboxes, learn about the drive shafts, learn about the propulsion and all that, to learn how they all put that together, that aircraft together. And that's going to be the theme of my first paper. On the second paper that I'm planning to write is going to be related to the variable stability system, as I mentioned earlier. That's another area of research that I got to dive into, which is a little bit more complex than just going through the mechanical parts, okay? But notice that I have when I have nothing better to do, which is never, I'm going to sit down and try to go through those drawings one by one. I'm going to spend probably a whole year just looking at those, if not more. Niagara Falls Aerospace Museum, apparently they don't have a deadline for me to return those drawings. So I'm going to try to keep them as long as I can, hopefully for a couple of years before I return them to them. And they were very gracious and very nice to be able to do that to me. And that shows that they care, like Paul Faulting and all those guys, they do care a lot about history. And I really appreciate their efforts in loaning me this information. I'm taking good care of it. So I'm going to return them back to them in due time. Next slide, please. I wanted to show this picture, which is bringing me a lot of good memories from the past. You can see there on the left. I'm going to start with our friend, Mike Hirschberg, looking very young there. I wonder how Mike looks today. He probably looks very old. He doesn't look like that anymore. No, just kidding. Just still look great.
I spit an image of him. Spit an image of his younger self.
You still look wonderful, okay?
That's cool.
So that picture shows Mike. He hosted all these folks, which you probably don't know, but I'm going to tell you who they are. You can see the names down there. Hannes Bala, a good friend. I haven't heard from him in a while. I sent him an email last night trying to figure out where he's at and what he's doing these days. Hal Andrews, who is passed away. This man was a project engineer on the X-22 on the Navy side at the Bureau of Weapons. That man is, we owe a lot to him. He really did a lot for our history, a lot for our research on our history. He really was an archivist, historian, a great engineer, you name it. Mike Hirschberg had the pleasure of knowing him. I got the pleasure of knowing him a little, but Mike really got to be his friend. And that's something that it should be treasured by all of us. Also, the same with John Snyder. As you know, Paul Farding received the award for the historian award for due to John Snyder. John Snyder, obviously the head of Vanguard, which, by the way, Vanguard was a intern on the tri-service program. They put out a project or a proposal in response to the RFP of 1961. So John Snyder was not only an incredible historian, he was also an incredible engineer. And he actually founded his own company. I mean, these people are our forefathers, the people that we need to look up to. And on the right side there, you have Hal Flock, who was involved in the X-19 program. I don't exactly know his role. I'm still trying to research out a little bit. Again, I got all this information in my books and my binders and my papers. It's just that I cannot do everything. Mike, do you remember what his role was in the X-19 program, sir?
He was flight controls, but I'm not sure. He did publish a book shortly before he passed away on the X-19 and the other Curtiss-Wright tilt propellers.
Yes, I do have 2 books on these aircrafts, and they are great books, great references. I got a picture of myself holding the Bell quad aircraft there. It was a quad tilt rotor, but it more or less was similar to what Hal Flock had to deal with on the X-19. So the bottom line is that all these folks, which are now, unfortunately, some of them have passed away, I really want to dedicate this presentation to them, because without them, we wouldn't have anything. They're really our forefathers, our friends, our mentors, and God bless them all in heaven for that. Next slide, please. And that's it. Thank you very much.